Okay, so welcome everybody. This is my first time at the ICTS, and I'm really impressed actually by the campus. It's really amazing, and by the lectures. So I hope it will be also good for you. The ones I'm going to give is about positivity bounds on effective field theories. This is the title. But actually, so at the beginning, I thought I would discuss directly the state of the art going by using the special relations arguments. But since you already had a class last week, I thought I would discuss first another aspects related to positivity, which is causality bounds on effective theories for the first couple of lectures, maybe 2.5, and then to see how they are connected to positivity bounds. Such a way you will have a complementary view on the subject. So the rough plan is the following. So this lecture, the first lecture is basically only motivations. Motivations and examples. In a sense, why bothering about causality / positivity? And in a sense, I will try to argue that in analogy with the string theory landscape, there is a sort of quantum field theory landscape as opposed to the swampland. And that if you naively follow the rules you're learning about effective field theory, most often of the time you would land discussing a theory which is actually in the swamp, but it has no parent theory in the UV that will produce it along the RG flow. So we're interested to see whether you're missing some ingredient that a good theory in the infrared should have, and also to be the parent infrared energy limit, sorry, the daughter low energy limit of a parent consistent quantum field. This is more or less the plan for today. Okay, maybe also I will contrast NDA and symmetries on one side versus causality, and see whether there is something beyond these two ingredients. And then, well, perhaps I will also mention the relevance of this reasoning for phenomenology, colliders, for example, or even beyond, even for example, in theories of modification of Einstein-Hilbert gravity. So this is the plan for today, mostly about motivations. Next time, we start discussing causality constraints in detail by examples. Particularly, we discuss example effective theory for U1 Goldstone bosons, theory of photons in the deep infrared, and exotic theories like Galileans, and so on. Then we discuss causality in gravity. So particularly we discuss whether we can have time advance in EFT of gravity and how to build time machine in case. Which clear contradiction, and the theory would not be good. And then the question whether, well, there's a technical question I will address, which is about resolvability of time advance This probably will take us 2 lectures, actually. And the third lecture will move to actually positivity. Yeah, dispersion relations. So how is connected the causality? In particular, we derive the explicit connection and how all this bound can be recasted directly in terms of dispersion relations. And well, we go through again the same example, but with a new angle on the topic. And so this is probably 2.5. This is another lecture. So the last lecture is going to be about connecting positivity, material moments. We will see that, in fact, there are infinitely many bounds. On Wilson coefficients. Of course, infinitely many bounds doesn't mean they are infinitely powerful, because most of the time you cannot even access, perhaps most of the time you can access the first few. So having infinitely many bounds perhaps doesn't buy you much. But it constrains the structure of the theorem. Okay, so let me start with motivations and examples and why you're bothering about this topic. So yeah, you already heard it twice, I think, or maybe 3 times today, that broadly an EFT, I think it's worth repeating it. So the EFT is basically broadly defined by the Lie degrees of freedom, the symmetries, and of course the basic principles. You never drop, like, quantum mechanics. Word is quantum mechanical, so by this I mean you get RG flow, you get unitarity, you get, well, in a sense, also, well, so these two already will give you some constraints on the structure of the effective field theory through what you would call the NDA analysis. Okay? For example, the size of an operator in the infrared should be consistent with the way it's normalized by other operators, for example. These are the basic things that you are being learning in this school, I think. And they are very important, absolutely very important. Of course, here by symmetries, there are all sorts of them. Okay, there is, of course, it's Poincaré. There are internal symmetries. It could be approximate, perhaps, or anomalous. They are all important, actually, right? So accidental and so on and so forth. And one important aspect I want to stress here is that as soon as you combine quantum mechanics with Poincaré, you know that the Lie degrees of freedom here are basically, basically you have to specify 2 quantum numbers. You have to tell the mass and the spin of the states you're talking about because of Poincaré and quantum mechanics. And so when we discuss Lie degrees of freedom, is light compared to what? It's compared to the degrees of freedom, which are not relevant for the experiments you are interested in. So we're going to assume there is a mass gap between the Lie degrees of freedom that describe the system and the scale. So this would be going to be a scale where new degrees of freedom arise. So this is a physical scale, okay, where new particles can be produced on shell, for example. In particular, this one is typically smaller than what typically is called the strong coupling scale, which is when the effective field theory becomes strongly coupled. You are no longer able to make predictions. These 2 scales typically are not the same scale, and there are plenty of examples. So maybe I want I give you one. Take, for example, Fermi theory. Theory of fermions, low energy. So dimension 6 operator. And well, this gives you amplitudes for 2 to 2. For the fermions, they go like energy over F squared. So the amplitude becomes large, so T becomes strongly coupled, while the energy is 4 pi F. So in this case, lambda strong will be 4 pi F. Of course, it's not where, in actual, for example, Fermi theory, that's not actually where new physics show up, right? It shows up rather at the W mass or the Z mass, right? So it happens much earlier. It happens at a scale which is G times F, where F is the Fermi constant. So as long as G is small, which is the case in nature, so this K is much smaller than this. So typically, often we trade this scale for this scale just because we don't know where new physics may show up. This is an upper bound. This is an upper bound where the new physics is supposed to be showing up. And that's why often one refers to this scale as the cutoff. But really, the cutoff is this one, where new degrees of freedom appear. Just that if they appear before this scale, the UV completion of your EFT will be weakly coupled. Okay, so let me draw the following picture. This is energy. And we are going to study the effective theory of low energy, so living in this plane. So this is the space of EFTs. So there is some scale M here, where the space of quantum field theories that evolve at low energy. I give you some point here in the space of effective field theories. And this map defines the space of EFT, which I would say are what I would say they are in the landscape, or quantum field landscape. So they are emerging from some underlying consistent quantum field theory. However, well, maybe let me give you an example. Of course, here there is the chiral Lagrangian. For example, a parent theory here would be QCD, or it could be Einstein-Hilbert gravity here. The parent theory, for example, would be string theory, which is not quite a QFT, it's a subset here of quantum gravity theories. The string theory, or in the case, for example, Fermi theory, here would be Yang-Mills, then you get Fermi here, and so on, right? But there are, if you follow the basic ingredients here, you will soon realize, and I will show you an example, that you're going to populate. Basically, these axes are basically Wilson coefficients. You're going to populate regions for which you have never seen a UV completion of. So an example, if you deform the chiral Lagrangian, for example, there's a deformation that brings you here. This theory is called Galilean. And you will see that doesn't, because of causality, you will see that doesn't come from any microscopic consistent theory. Likewise, for Fermi here, there's a deformation. Well, there are two deformations. There's one that brings you still inside. It brings a theory of Golstini, or Golstino. So low energy squared symmetry, spontaneously broken, is a theory of fermions, which is massless because they're breaking a symmetry. And that's perfectly consistent. But there's another deformation that brings you here. And we discuss it. Basically, it's a theory where the fermion has a shift symmetry in terms of a Grassmannian constant, psi. And that theory is going to respect all these principles. Nevertheless, it doesn't come from any parent theory. So, and likewise for Einstein-Hilbert, there's a deformation here. Well, there are many deformations that keeps you inside. There's one that brings you outside here. which is when you are adding, for example, Riemann cube. So this one comes with 1 over G front, G Newton. This one, if you're taking this coefficient, this operator very large, also it will put you outside this. There's no string theory here that will produce an operator with a large coefficient in the units that you would naively expect. So it seems there is a yeah, that's the way I define it. Yeah, is the RG map of a theory which we know is consistent. So yes, everything here is going to have a parent theory by definition of this. Instead, outside, we will see, we will find another ingredient missing here. Perhaps I can add it, plus the missing ingredient is this one, and this is going to kill this guy, this guy, this guy, this guy, and many others. So in a sense, is a transverse direction to these basic ingredients to build effective theories. Okay, let me try to, okay, or maybe let's say it again. So we're going to use causality in a sense to shape this boundary. Okay, we're not going to shape it completely. It's just one ingredient. Perhaps there are many ingredients that we are missing. Right? We are going to show that just this one is already good enough to rule out theories that would respect otherwise normal power counting, normal EFT reasoning. So it's an interesting observation. But it could be more. Of course, it could be more. For example, quantum gravity, you expect many more conditions, for example, to be satisfied. Right? Yeah, big gravity conjecture, or the no global symmetry conjecture. So all of these are expected to be additional constraints on top of the causality conditions that I'm going to mention. So let's try to make this picture a little bit more concrete, and let's explore some theories by looking how they behave with energy. Okay? And let's look at the scattering amplitude for 2 to 2. First, in the simplest case, first is going to be for a scalar. So I'm going to take it massless, meaning or light. For a scalar, doesn't matter much the difference, and a spin 0. Okay. I'm going to try to parameterize what I can get in infrared by the behavior with energy of this amplitude. Okay, so can definitely be constant, right? So amplitude for energy. By the way, I'm gonna look again in this regime. Perhaps energy much larger than the mass. I'm gonna discard mass effects, but much smaller than the new physics scale, so I can have a sensible expansion in derivatives, for example, in energy derivatives over the mass scale. However, the theory that completes this amplitude can be perhaps strongly coupled at the scale m. So the constant case, do you know an example? So let me put here example of that behavior. So what amplitude gives you for phi phi to phi phi lambda? It just, this definitely lives here. Okay? We have a theory up to the Landau pole, perhaps. So it's not perfect, perhaps not consistent all the way to arbitrary high energy, but exponentially large relative to the mass. So it's pretty good theory. We can have a faster scaling with energy. You have an example of this. You scatter 2 scalars, you get 2 scalars out, and the amplitude grows in the infrared. In the infrared, low energy grows, or if you want, it decays from the perspective of the UV, lowering the energy, it decays with E squared rather than being pretty constant. So you have an example of this in mind? Pi scattering, yes. So Carrier-Lagrangian is an example, right? Things like this. 2 derivatives for fields, dimensional analysis, there is a scale, got a term. and you hit this theory. Maybe the only non-trivial part here is that you need more flavors. Just one boson here will not be enough. Okay, let me call this pi as well. So what if, so this one can be selected by a symmetry, right? So you have seen, this is a chiral Lagrangian. So there's a nonlinear symmetry that selects this one, whereas this one breaks the symmetry. So it's completely natural to have a small parameter here relative to this one, right? If I say this is the leading interactions, and this one is subleading, that's perfectly okay, right? There's a window. If I look at, if I had both, this is an approximate symmetry. If I had both, the amplitude will scale like, well, epsilon plus square over f square. And therefore, there is a window for energy sufficiently large. So I basically want this one to dominate over this one. And there is definitely a window below the scale m. And this can happen as long as epsilon is very small. If epsilon is order 4 pi, there is no window, of course. This is order 1 away from this one being a good symmetry. There's no window, but as soon as this one is small, you have, well, basically E has to be larger than epsilon f. If epsilon, so let me write this way, epsilon, let me call it epsilon square. Epsilon f has to be big energy in this range. As long as this one is less than 4 pi f, so epsilon is more than 4 pi, I'm in business. So I can trust these effective theories. So let's go next. So this one definitely looks living here as well. So let's see e to the 4th or f to the 4th here. Let me call it maybe. So what theory will give you this behavior? Also naturally so. I can always maybe fine-tune things, try to kill this one. I want this one to be the leading operator. Of course, to be leading, this one must be suppressed, very much like for this one to be leading, this one had to be suppressed. Here I use a symmetry argument. So I'm using symmetry argument, one of the ingredients. So what it would be the symmetry here for this one to be the leading? Single flavor shift symmetry, which is associated to a U1 Goldstone boson, precisely selects that behavior. Right? The Lagrangian invariant of the symmetry. First of all, kinetic term is invariant. And this term is also invariant. It's the first one which is invariant. So this one is going to dominate the amplitude. So it's going to give you this one. Since it comes from a U1 Goldstone boson, it's very simple to write a UV completion. Okay? It's the Higgs model without gauging the U1, such that these Goldstones are in the spectrum. So these also live here. So the Goldstone boson, the U1 Goldstone boson also live here. So there is interesting observation here is that this coefficient here in front turns out to be always positive in any model. Of course, in the EFT perspective, this is unconstrained. So respect the symmetry can have either any sign from the point of view of symmetries. But if you try to match it to any UV completion, you always find it positive. So that we will see this is the trademark for causality. That the strict sign here will come from causality. A simple example, if you try to UV complete the scattering of this Goldstone exchanging a Higgs, right? So the Higgs is a propagator, there is a propagator here. And therefore the sign of the, so there's a d pi here. this design is completely fixed and you cannot change it. That's why you land in alpha positive. But do another example, you generated one loop, integrated out fermions, also positive. You look at Brennons, you have brains in, so 3+1 brains in 4+1 backspace time, fluctuations of the brain. Here are a scalar degree of freedom. You always get this as a effective theory with a positive coefficient. And in this case, it's linked to the positivity of the tension of the brain. So next example, e to the 6. Is there a theory that produces e to the 6 kills this one? It kills the constant by symmetry. This one, and the first leading operator is this one. So notice, you have to be cleverer than clever, right? So no thinking, constant. Some thinking, e squared. Well, this one probably comparable amount of thinking, but then here, so there is a symmetry. So you shift your scalar field by a constant and also a linear monomial in the space-time variable x. So basically, d mu pi shift by a constant. That's the symmetry you're demanding. So clearly the invariant, the trivial invariant would be, in this case, would be dd pi. dd pi is invariant. So if you write down the simplest example would be a theory with dd pi to the fourth. So 8 derivative will give even faster than this. We'll go like e to the 8. Right. In fact, you see, I didn't write the kinetic term here. What about the kinetic term? Is it invariant? Well, it's almost invariant, right? It's invariant up to a total derivative. So this is good. It's a good symmetry. So I can write the kinetic term. In fact, there are other terms I can write down. For example, this one is also invariant up to a total derivative. You see, it has 4 as so it's a trilinear, first of all. So it's a type like this one. So to build a 2-to-2 amplitude, I need 2 insertions. So I'm gonna get 8 derivatives. Then I have a propagator here. This one is gonna give me e to the 6. So this is called the Galileo interactions. And I keep going, right? I can do, okay, e to the 10, where I'm gonna ask that the invariance is under a shifting by a polynomial, which is quadratic. Because it's getting weirder and weirder. So admittedly, but I'm saying that nothing will seem to stop from the point of view of symmetries here to write more softer and softer interactions. Except that nobody ever have found a V completion past this line here. So all these theory here, even though they respect all the symmetries that you, and all the reasoning EFT that you would apply here, apparently there is no UV completion for them. And the reason I'm going to argue in the next lectures is that this theory and the one with more derivatives as leading will violate causality in the infrared. So indeed, there is a missing ingredient that you should pay attention. Questions? Yes? Yes, so, but from the point of view, the amplitude here, so this boundary condition is completely innocuous. And well, moreover, for example, if I build a symmetry which is invariant under this one, so there's nothing growing actually. Moreover, it can be an approximate symmetry. Okay? The deep infrared, I go very, very large distance, I'm actually not dominated by this one. I may be dominated by this one. The deep infrared, this one is not leading anymore. It's leading at intermediate scales, below M and above some energy threshold. Very much like in this example. Okay, so let me give you now another couple of examples. Let's take M equals 0. With this, perhaps you can think, okay, this is a, who cares? I mean, scalars.
Hi, Brando.
Yes.
This just a clarifying question. Might have already explained this. Your simu is a constant vector, right?
This one is a number. It's a collection of numbers.
So doesn't it break Lorentz invariance for you?
No, it doesn't. Look,
It's a spurion of breaking Lorentz symmetry, no? Because it's.
I explicitly write down here the Lagrangian. There's no explicit breaking of Lorentz invariance. Look, it's invariant, no symmetry break.
Okay.
So let's do maybe a more physical example. Well, perhaps maybe I want to say something more maybe before that. This looks like exotics. I mean, it definitely is exotics. But for example, if you try to discuss effective theory for massive spin 2 particles, when you go in the energy limits where the energy is much larger than their mass, basically they behave like a collection of theory with Gaussian bosons. And one of them is the Galilean. Okay? So for example, the effective theory for a massive spin 2 particles includes the Galilean at intermediate energies. And in fact, because Galilean break causality, that is going to be a reason why you have never seen isolated massive spin 2 in the spectrum. Basically, the effective theory has to break at their mass. You can never go to energy much above their mass. Okay, let's go now to this example. So light particles, particularly now 0 mass and spin 1. If the mass was different from 0, let's say epsilon. So at the moment I didn't, it's just by example. At the moment I just tell you is as a fact by model building. You build a consistent model, you run it down in infrared, try to match it to the EFT coefficients or your Gaussian bosons in this case, you always see that's positive. And we will see that the underlying reason is that the theory, the microscopic theory you started with, is causal. So we will see, I mean, the point of these lectures, the next lecture is going to be to show this, why alpha has to be positive. At the moment, it's just an experimental fact by experimenting and building consistent theories. So, let's take a massive spin 2 particle described by a 2-tensor symmetric traceless field. And this one, in the energy limit, it contains polarizations that behave like a scalar field with 2 derivatives acting. Very much like for a massive W, at the energy, the longitudinal polarizations behave like the derivative of a scalar field. Well, 2 derivatives is precisely what make him build invariants under the Galilean symmetry. So that's where the Galilean symmetry comes from. So as soon as you have a higher massive spin, you run in these weird objects. Okay? In fact, one of the I would say nice thing of this program in the last few years was to show that there is no, maybe I forgot to mention here, there is also massive higher spin theory isolated. Only one. Only one at the bottom of the spectrum, that is parametric separation from something else. This one is in this one plane. It's going to be exactly because of this reason. Because the longitudinal degrees of freedom behave like scalars with these weird symmetries. It's going to be violated by it. It's going to be inconsistent with causality. No, it is. I'm claiming the massive bigger than 2, spin bigger than 2, equal than 2. Absolutely. So vary the number of flavors, vary the number of colors, vary the number of species. In QCD, you will never get at the bottom of the spectrum a massive spin to particle hierarchically separated by other particles. The reason is not because of special QCD, it's because of causality. QCD, of course, is causal. So, okay, maybe to elaborate on this example, in extra dimensions, of course you get higher spin resonances, but they are all of the same order and the same mass. Indeed, perfectly consistent. String theory, the same. Okay, so the underpinning reason is causality. Okay, so m equals 0, j equals 1. Single species, let's call the photon, or photon-like particles. So the amplitude here, the lowest dimensional, so let's say it's represented with the vector, a mu, would be e to the 4th. Right? Indeed, the Lagrangian, with just this degree of freedom, okay, after energy below the electron mass, otherwise I would have the electron, also has slight degrees of freedom. So I have the kinetic term, and then I have corrections from integrating out the electron. Well, this will be the m here will be the mass of the electron to the 4th, 16 pi square. If it's loop generated, and then there's another one. There are two operators in this case. One alpha. Yeah, electric constant here. 16 pi square, electric constant, and to the 4th. You can match this number. These are order 1 numbers. You can match by looking at the UV completion of this theory. So scattering photon. If you go to energy above the electron mass, well, actually you're integrating in a loop of electron, but at low energy it will look like this. Again, these coefficients are positive. In any UV completion that match to this one at low energy, you always find this coefficient to be positive. Yeah. So these coefficients, which are the coefficient of f to the 4th and f tilde square, are always positive in all examples. And we will see that the reason, again, is because of causality. And notice that from the point of view of symmetries, it could have any sign.
Brando, sorry to bug you again. I didn't completely understand this aspect. So your pi and pi prime, the shifted pi, which is shifted by a c mu x mu, right? One of them doesn't transform like a scalar in Lorentz transformation, right?
This is not a Lorentz transformation.
No, it's not a lot. Well, I'm saying it's a symmetry transformation is a change of point of view, right? I mean, either you take pi or I take a pi prime. We should have the same thing. But one of them doesn't transform like a scalar, right?
You're bothered by the presence of x here, but
yeah,
scaling variance also involves x.
This, right?
Scaling variance also transform x. You can think of it as I mean, it's not an internal symmetry that the user type, but it's a.
I mean, the thing is that why I'm confused is if, we are saying that look at the Lagrangian and the Lagrangian looks invariant, but I do not know the Lagrangian is invariant if I do not know whether pi is a, Lorentz singlet or not.
Well, it is. You assume it is, and you check it. It is.
Right, but you write it in terms of a pi, and I write it in terms of a pi prime, where pi prime is shifted from you by this by c mu x mu.
Yeah,
and how do
you get the same Lagrangian because it's a symmetry. It's invariant. For example, kinetic term. The variation of L gives you d mu c mu. Integrated. Yeah. Or another term, this one. This one just is invariant.
You're saying that it's only contribute to the surface term, and so I am okay.
Sorry.
Okay.
Forgot to remove the alarms from going picking my kids from school. This one? No, sorry, when you say very large, it's 0, not large. 0. I mean, yeah, I think. But perhaps a more physical way is to think about, take a massive spin 2 and look at the properties of the theory in the energy. So massive spin 2 respects Lorentz symmetry. Look at the energy behavior above its mass, and you will see that the symmetry emerges as an approximate symmetry. I mean, of course, the whole point of this is to show that actually this is not going to work in the end. But it's not going to work. It's not going to work because of causality, not because it's not a good symmetry. In fact, in a theory which, for example, if you do a theory of a condensed matter, in Euclidean signature, that's perfectly fine. It would be a perfectly fine theory. So let's go. So this is an example of spin 1. So I gave you the one that goes like e to the 4th. We can try to do something similar to the Galileans. We can write a theory which has this symmetry instead. So where and if you demand that C mu nu here it's antisymmetric, well, if it's symmetric, it will be just a gauge transformation. By the way, this is another example why. For example, in this case, if you take C mu nu symmetric, this is just a gauge transformation. It's a large gauge transformation. Instead, if you take antisymmetric, is a shifting the F mu nu by a constant. So the effective Lagrangian in this case would be something like, well, again, the kinetic term would be invariant up to total derivative. So it's allowed. Then you get the first interaction term will be something like this, with various possible contractions. So 3, 12, need m to the 8. So this one will give you an amplitude that will scale like e over m to the 8th power. And so it's perhaps no surprise at this point, there is no UV completion. That does that. Even though you have a symmetry argument to kill the Euler-Heisenberg term, and have this one to be leading. much time do we have? 10 minutes. Okay, then I guess I skip the fermion example. Let me give you an example with gravity, which is more instructive. Let's take the following effective theory for gravity. So I have a Planck square, Einstein-Hilbert term. Now you add higher derivative terms. This one, well, of course, it is also quadratic, but it happens in 4 dimensions. In 4 dimensions, there will be 3 of them, but 2 you can remove by a filter definition, moving it to higher terms. The 1, which is a Gauss-Bonnet term, is not going to affect the scattering amplitude, so I'm not going to write it. Instead, in higher dimension, it would matter. So this one has 4 more derivatives than this, so there's an L to the 4th here with some coefficient alpha 3, and then be Riemann to the 4th, right? The 6 with some coefficient. And if you look at the amplitude, scattering gravitons, you get, so the leading term will give you an amplitude that goes like m Planck squared, e squared, from Einstein-Hilbert term. Depending on the choice of polarizations, you get corrections. These guys, you get alpha 3, e over m, the 4th, and so on. So you see, there is a small. So if you let's assume the following. Let's assume we are discussing a UV completion of gravity, which enters much below m Planck. We're considering energy much below that. So there's a weakly coupled UV completion. At energy m, this prefactor is very small, suppressing all the amplitude. So what will stop you to ask, is it possible to have alpha 3 much larger than 1? Is it possible? Given that this is small, this is very small. So there's nothing wrong with the perturbative unitarity here if I take this, for example, 10, 100. If this number is 1 over 1,000, for example, can I take this to be 100? The amplitude will be still very small. Is it possible? So from the point of view, there is also a symmetry that does that, which I'm not going to discuss. So there's no string theory example where this happens. It's never possible to take this much larger than 1, even though from the, for example, perturbative unitary perspective would be possible. Well, and the reason, again, is causality. Is it clear, this example? I couldn't even tune, but I could just fine tune it, try to fine tune it. You'll not be able to do it. It's an abstraction. And I don't want to phrase it as fine tuning because I'm just looking at theories fine tune. Why am I? Okay, so instead I'm telling you there is even a symmetry that will allow you. Even in this case, there is a symmetry, which is an approximate linear diffs invariant. This that Einstein breaks, these are respects. So you would be able to do it in principle to generate m much smaller than m Planck and having this suppressed. But okay, regardless, even trying to fine tuning, you will not be able to do it because of causality. Okay, so maybe after all I can do the fermion example. How much time am left? Okay, so gravity was quick. Okay, maybe on the gravity side, I will maybe add one comment. You can even, you can do, So this was a perturbativity statement. So what would go wrong if I take this much larger than this one? From the point of view of perturbation, there doesn't seem anything to go wrong. However, in this case, this particular case is a bit different than the rest, because if you do the estimate of the size of this one by NDA, for example, you try to integrate out some matter coupled to gravitons, so generate a Riemann cube. You try to do the estimate, you will land with the alpha 3 at most 1. Okay, we can do it. For example, this one, if the matter is coupled with strength 1 over m Planck, of course. If it's coupled more strongly than that, it will be different. So you will get 3 powers of m Planck. You will get an integration of the loop momentum. Then you get 3 propagators. Then you get 3 vertices, which couple to T mu nu, so it grows with the momentum. And then you have to be sure that you are selecting Riemann cube here. Riemann cube has 2 derivatives. So you have to remove here 6 powers of k. So this one is IR divergent, so it's cut off by the mass of the lightest particle, which are this particle in the loop. So this one is going to give you 1 over m Planck cube, which I'm going to, well, let's say ddh cube, 1 over m squared, 16 pi squared. And then perhaps if I have n species, I will get a factor of n, perhaps. Now I go in the canonical basis where I have an m Planck here rather than canonical normalization. I reabsorb the m Planck here. So this one gives me Riemann cube. Now I normalize it by taking out an m Planck square here. So you see that indeed, so the alpha 3 coefficient is actually m square over m Planck square times the loop factor. So I can enhance the loop factor almost to 1 or 4 pi perhaps. So, and m is more than m Planck by assuming I have the perturbative UV completion, or almost around m Planck. So this is actually bounded by 1. Okay, so in fact, relative to the previous examples, it seems so hard to construct something that would make it bigger than 1. However, suppose you started with something which was bigger than 1, you're renormalizing it by a small amount. Where is it? Here. So it would be consistent. As long as this one is smaller than the scale you started, it's okay. It would be a problem if it was smaller than this one. That would not be consistent with NDA. As long as it's larger, it will be consistent. But nevertheless, you find there is no UV completion for that. So the whole point of these lectures is to show why this is happening, even why these 3 basic ingredients are not enough. Why you need to add this one more. Okay, in the remaining minutes, I want to also tell you that this is interesting also for phenomenology. So far I just discussed space of theories, which of course is interesting because we haven't seen any new physics so far. So we're trying to parameterize the space of what can we possibly get. Are we missing something? Are we missing crazy theories, which however will have a nice power counting? So that's the way I was thinking about this program. But another reason is phenomenology a collider. So take a standard model, and you deform it with the eigendimensional operators. So the standard model, low energy is controlled by dimension 4, so you're going to add those larger dimensions. So if you, as like Tim Cohen said at some point this morning, you need to assume something about the UV. So if you assume that the leading operator is going to show up in dimension 6, indeed, searches will put a bound, for example, I don't know, composite fermions. Composite fermion will come with some coupling, some scale. You will put bound. You would say this is a dimension 6 operator. You will put bounds of this type. The energy that you probe at experiments, this one should be smaller than some experimental accuracy. Right? However, imagine, now let's do another UV assumption. Let's imagine that instead, this is not leading because there's a symmetry that forbids it. For example, there's this symmetry. So such that the invariant is built with a spinor and a vector. So the first operator with 4 spinor you can write down is something like this. For example, would be this one. Chi dagger square box of chi square. So as 2 more derivatives relative to that one. So it would have here the mass scale to the 4th with some coupling squared. So the experimental bound would be weaker, right? Because now you will get G star square of this weird theory. By the way, this is the operator you get for Agostino's. Agostino has precisely the invariance under this. So you will get here that energy experimental and to the 4th here should be smaller than, for example, you can use this one. So the experiments at LHC will tell you that your coupling divided by the mass times here could be the energy of the cut you're doing your analysis should be smaller than something because you haven't seen anything. Well, the bound relaxes pretty much. If you have a symmetry that forbids the leading operator, you go to, well, the would be leading. The actual leading happens to be dimension 8 in this case. The bound will be much weaker. And so in fact, you can imagine that, so this is an amplitude. This is where new physics is. The amplitude has to be smaller than some region here, probed by experiments. So if your coupling was here, so it runs with E square, you hit the boundary here, you get a constraint on how large the coupling can be or how far the mass can be. They enter in this combination, coupling over mass squared. But if it scales faster, it can be closer because it decays faster. So the bounds on the coupling weakens very much, or the mass scale can be closer. It runs quicker, so you reach the same point even though it starts earlier. For example, you can relax easily by a factor of 2 the bounds of compositeness if you assume, for example, that the fermions are invariant, are partially composite and enjoy that asymmetry of the sort. So in fact, here I'm cheating a little bit. There's an extra term here. This is for the Agostino. That's a perfectly good consistent theory in the infrared. If you don't put the extra dots, so you can see the difference in the nodes. The actual invariant would be with even more derivatives. It would be something like this. This one will run even faster with energy, will be even less constrained from LHC data. However, this one, it runs so fast with energy that again, it will be at odd with causality. So in a sense, what causality tells you is there are only 2 types of composite fermions. There is either this one or the one that starts at dimension 8. The one that starts at dimension 10 is not a thing because of causality. So you see, well, the point I want to stress is that causality buys you something also for phenomenology. You can try to be smart, inventive, they have a super weird symmetry, the last dimension 11, dimension 12. No, causality puts a boundary. So up to the leading must start at dimension 8, the latest. It can be earlier, but the latest must be dimension 8. That's the subject of this class, of these lectures, and we'll see the beginning of this tomorrow. Are there questions? No. Well, so well, we will see. We will see this. We will see explicitly an example where this is not doesn't happen. If you break causality if this one happens to be negative. Could be besides, can be even teeny tiny. Can be epsilon negative. Can be 10 to the minus 10 negative, ruled out. So relativity is not a statement about causality. Relativity is a statement about the group of symmetries of the laws of nature. Okay? That's causality is a different statement. That's precisely. Lagrange is divided under certain symmetries, but it doesn't mean that you're not able in a theory that respects the symmetry to build, for example, closed like time curves. You can, if you have the wrong sign. That's what I will show you tomorrow. Besides, there are plenty of examples in GR. You can build time machines. Something must go wrong. For example, in GR, often is that you are having state with negative energy. So it's more than general relativity. It's a further statement. I just suppose.